So now let's look at another case of non-ideality where we go far enough into forward bias that we start injecting large concentrations of electrons into the p-type side and holes into the n-type side. So we're really talking about regions of high forward bias over here. So if we come back to our sort of schematic drawing and we write out the concentrations at different points. So far away from the interface between the quasi-neutral region and the depletion width, the concentration of electrons on this side, minority electrons, is NP naught here. Now, we're injecting minority electrons. So at the edge of the depletion width, we have a voltage-dependent boundary condition where we're injecting this many carriers. And this is, remember, the total. So if we use the breakup of the total concentration into the thermal equilibrium plus excess carriers, we can then write the concentration as this expression. And of course, this is where the expression for the ideal diode current comes from. Now let's take a look at our NP product in this junction, and especially in the region just next to the depletion width. So NP without any bias and under thermal equilibrium is given by Ni squared. Now, if we break the equilibrium and go into a steady state condition, we could have N naught plus delta N and P naught plus delta P. And if we're injecting excess carriers, what it means on a band diagram is that we've brought EFN and split it away from EFP so that we have delta N up here and delta P here. So they're, both Fermi levels are split away from their thermal equilibrium values. And it turns out that the Fermi level splitting actually modifies this expression. So by manipulation, we could get this into a expression that reads like this. EFN minus EFP over KBT is going to give us a modified NP product that we can use under steady state with excess carriers present. So then let's take a little look at the Fermi levels as a function of distance on both sides of this p-n junction. So under bias, it turns out what we're doing is splitting these quasi-Fermi levels. So if we look far away from the junction on the p-type side, we have EFP here, and we have EFN here on the n-type side, far away from the junction. And the voltage that we apply turns out to be equal to this quasi-Fermi level splitting. So therefore, we can rewrite this as Ni squared exponential to the applied voltage over V thermal. Now, what happens to these quasi-Fermi levels, inside the depletion width and then just outside it? Well, our assumption that the carriers do not disappear or recombine inside the depletion width means that the quasi-Fermi levels should be constant. And actually, I should draw this in blue. There we go. So that means we should continue the Fermi level from each side horizontally like this. And then we have an exponential decay in the number of excess carriers on both sides. And that decay occurs over the diffusion length. So what that tells us is because the quasi-Fermi levels are related logarithmically to the carrier concentrations, it means that the quasi-Fermi levels change linearly on this graph versus distance. So the EFN linearly decays back to the equilibrium value of EF far away from the junction because there's no excess carriers out here, and similarly far away from the junction, the Fermi level has to return to its value on the n-type side over here. Okay, now we're in a position to discuss what happens under high injection. So let's define our high injection conditions first. So looking at this expression, when quasi-Fermi levels are split, the NP product is modified to this form here. So we have NP equals Ni squared exponential to the voltage applied over V thermal, because we're splitting the quasi-Fermi levels by the application of an external bias. So now this is N naught plus delta N times P naught plus delta P equals Ni squared exponential of V over V thermal. So in high injection, we can assume that these are bigger than these, and then by taking a square root, we can conclude that delta N should be about equal to Ni squared exponential to the V over 2 V thermal, with the 2 here coming from the fact that we took a square root. And the square root undid that too. So with this as our expression for the boundary condition here under high injection, what we see is effectively we've introduced an ideality factor of 2 here. So let's look at this JV curve now on a logarithmic scale and look at 3 regimes of behavior.